Hey gang, so last week it was announced that two teams of physicists had finally discovered proof of gravitational waves, and the physics community went wild! This is probably one of the biggest scientific discoveries of my lifetime, and it's going to have huge and far-reaching implications, both for physicists as well as astronomers. That's amazeballs! Now, what in the seven hells are gravitational waves? Most of us learned in school that it was Isaac Newton that first published a universal theory of gravity, essentially saying that the same force that caused an apple to fall from a tree to the ground also caused the planets to stay locked in orbit around the sun. We tend to visualize this by imagining a weight of some sort tied to a string and a person spinning that weight around. In this case, the string represents the force of gravity pulling the weight back towards you, even as the momentum of the weight wants it to go flying far away. For the most part, this does a good job of describing gravity, and describing the behavior of objects that are under its influence. But it's also incomplete. In the early 20th century, Einstein showed with his special theory of relativity that the speed of light is a constant, and that nothing can go faster than the speed of light in a vacuum. This is a problem for gravity. The reason being that if we go back to our example of a person spinning around a weight on the end of a string, if they let go of that string, the weight goes flying off instantly. If we go back to thinking about this in terms of the planets and the sun, that then would mean that if the sun were to suddenly disappear, the planets would also instantly go flying off. But remember, according to relativity, nothing, not even gravity, should be able to move faster than light. And so we had a problem. Einstein eventually solved this problem with his general theory of relativity. He said that rather than thinking of gravity as being like a string pulling on a weight, we should instead think of it as being something like a person sitting on a trampoline. If you try and walk past that person on the trampoline, inevitably you're going to be drawn in towards them because the trampoline is curved in around them. In other words, gravity doesn't so much pull at objects as it does change the shape of the space around them, curving straight paths in towards more massive objects. So this is where gravitational waves come in. Think about what happens when people move around on trampolines. They create ripples that spread out across the surface of that bouncy fabric. Likewise, one of the predictions that comes out of Einstein's theory is that massive objects moving through space should likewise create ripples in the fabric of space itself. The problem here is that space is a really big place, and that gravity is a surprisingly weak force in it. It would have to be, because otherwise the entire universe would be collapsed down to a single point. In order to detect them, we would need a massive event that creates some pretty huge waves and some incredibly sensitive equipment to detect it. It's taken 100 years for us to develop equipment this sensitive. Here's how it works. First, we need to understand what gravitational waves actually do to space itself. To do this, imagine that you yourself are producing gravitational waves and sending them out towards the screen of your computer. Now, the objects on that screen would start to stretch vertically and horizontally, going back and forth as though trying to draw out a plus sign, but the screen itself would stay in place. It wouldn't go back and forth. This is called quadrupolar wave propagation. In order to detect this type of wave, you need a special instrument that's called an interferometer. What it does is it takes a laser beam and splits it into two parts that go off at a right angle. Those two beams then are reflected back together at a detector. Because seismic waves are so much more powerful than gravitational waves, you also need to isolate each of these components from any kind of seismic interference. Now, all things being equal, the two parts of the beam are in phase with each other, so when we bring them back together, they should cancel each other out, like dead zones at a concert. The detector would see nothing. If, on the other hand, a gravitational wave was going through the equipment, we would see those mirrors start to bend back and forth, just like the objects that we saw stretching on screen, right? Now, because the two mirrors are at a right angle, one of them is going to be stretched farther than the other one, and that's going to mean that the beam that is going down towards that mirror is going to have to travel ever so slightly a longer distance than the other beam. By the time they come back together, they'll be slightly out of phase with each other, and thus we'll get an interference pattern rather than nothing in the detector. And when I say ever so slightly, I mean barely measurable. Each arm of the interferometer is 2.5 miles long. The difference in distance they're trying to measure is less than the size of a nucleus of an atom. Even then, the signal is still really noisy, so the scientists that detected these waves essentially had to be looking out for some very specific bursts in it. They had to develop some very specific models in terms of the waves that would be produced by a number of different cosmic events. They would then have to match up those models with all of the noise that they were getting out of their detectors to try and see if they could make a little bit of signal stand out in there. You can think of this kind of as like if you're walking down a busy street and you want to check in on the score for your favorite game. You want to keep your ear out for that high tinny sound of an announcer on a radio. That way you can sort through all the noise that you're hearing on the street and get the information that you want. The experiment to detect gravitational waves is called the Laser Interferometer Gravitational-Wave Observatory, or just LIGO for short. It involves more than 900 scientists all across the globe, and it is the single largest experiment that has ever been funded by the National Science Foundation. So why is this a big deal? Why is the physics world losing its mind right now? Aside from the fact that it is awesome that this experiment was set up in the first place, It also has huge and vastly reaching implications both for physics as well as astronomy. For one thing, it's the first direct evidence that we have that gravity does indeed curve the fabric of space-time, thus confirming Einstein's theory. Now, we've known for the better part of a century that planets and stars move like we would expect them to based upon general relativity, but that's indirect evidence. We have never directly seen space curving until now. It's also a new tool for understanding the universe. For the entire course of history, astronomy has been more or less the study of the light that objects in the universe cast towards us. You could think of astronomy up to this point as essentially being deaf. With the introduction of being able to study gravitational waves, it's like we're able to hear the universe now too. So astronomy is able to use all of its senses to explore the universe. But what can we learn from gravitational waves that we couldn't learn before? Well, for one, they've confirmed the existence of black holes. Black holes are another one of those predictions that general relativity gives us, and we've had plenty of circumstantial evidence that says that they exist, but we've never had a smoking gun. By definition, black holes are dark. They're difficult to study by looking at light. But the gravitational waves that LIGO detected are so massive they could only have been produced by two black holes colliding with each other, and thus we have our first conclusive evidence that they exist. It's also likely we might find evidence for objects that we've never imagined before, or for things like dark matter or cosmic strings, but without a doubt the coolest thing this opens up for us is that we can see farther into the universe than we ever could before. Unlike light, gravitational waves can go straight through matter, and they lose their amplitude very slowly over time. This means that we can look through any object in the universe now and be able to see farther or see things that might have been obscured from our view before. So, I hope you've learned something here. If you've got suggestions for a topic in science or math that influences our daily news or everyday lives, please let me know by emailing me at drexplanations@gmail.com. Also, special thanks to my friend Jennifer Seiler for looking over the science in my script. Jen is part of the team that developed the models for what gravitational waves coming from two black holes colliding would look like, so the team at LIGO knew exactly what they were looking for and what they were looking at, so she knows quite a lot on this concept. Thanks so much for your help, Jen.